There is something wrong with our universe, or at least our interpretation of it. This week, news came out that a discrepancy within one of the fundamentals of our universe, the Hubble constant, isn't just an observational error. That means that somehow we have seriously misunderstood our universe. To be clear, we have known about this discrepancy, called the Hubble tension, for a while. But this week, JWST confirmed that the Hubble Space Telescope's measurement of this discrepancy were correct. This isn't just a problem with observations. Let's break down what the Hubble constant is and what all of this means. The Hubble constant is basically the rate of expansion of our universe. Ever since the Big Bang, our universe has been expanding at an increasing rate. Edwin Hubble figured this out in 1929 when he realized that the further a galaxy was from us, the faster it appeared to be moving away from us. This meant that the universe wasn't just expanding, but that the rate of expansion was increasing. This is thanks to dark energy. Understanding the Hubble constant is important for many reasons, one of which is that it gives us a good idea of the age of the universe, which is currently calculated to be about 13.8 billion years old. So, figuring out the value of the Hubble constant, something that is so important to understanding our universe, is probably simple, right? Well, this is actually a huge challenge for science. There are 3 different ways the Hubble constant can be calculated. First, taking a look at objects around us to see how fast they're moving away from us. Second, measuring small deviations in the CMB, or cosmic microwave background, which is light left over from the Big Bang. Or 3, looking at gravitational waves that are produced by the collision of massive objects like black holes and neutron stars. Measuring the Hubble constant any one of these 3 ways should lead to the same result, because it's a constant. But we don't actually get the same values from these different measurements, and that's where this discrepancy is, called the Hubble tension. Part of the justification for building and deploying the Hubble Space Telescope was that scientists hoped that it could give us a precise measurement of the Hubble constant. But instead, it has muddied the waters significantly. The European Space Agency's Planck satellite is mapping the universe's CMB. Cosmic microwave background is a relic of the first light in the universe after the Big Bang, which dates from about 380,000 years after the Big Bang. As the universe has expanded, it has stretched the light wavelength of CMB, which is why it's all the way at the microwave end of the spectrum. The longer the wavelength of light, the lower its energy. Planck has measured the Hubble constant as 67.4 kilometers per second per megaparsec. A parsec is about 3.26 light years, and a megaparsec is a million parsecs. So this is complicated, but it basically means that a space that's 3.26 million light years should be expanding 67.4 kilometers or 48.1 miles every second. The uncertainty here is less than 1%. But another method of measurement, visible observation of Cepheid variable stars, gives us a different number, 73 kilometers per second per megaparsec. Cepheid variables are very reliable stars that pulse in brightness on a regular schedule between 1 and 70 days. That makes them excellent for measuring distance from Earth because their brightness is directly connected to the duration of pulsation. Basically, the brighter the star, the longer it takes to pulse. The Hubble Space Telescope observed Cepheid variable stars very soon after its launch, and scientists used the observatory to continue to refine that Hubble constant measurement over the years. There's certainly a discrepancy between the Planck and Hubble measurements, but they could have been for various reasons. Dust obscuring the brightness of Cepheid variables looking brighter than they actually were because of an inability to distinguish them from other stars. The Hubble measurement could have just been some sort of error. But in 2022, a team used Hubble to examine multiple different distance markers, including Type 1a supernova. Cepheid variable stars are great distance markers for our local universe. But for further distances, these supernovae work better. They form when white dwarf stars explode. Because white dwarfs have to gain a precise amount of mass to collapse, that means that the peak brightness of any Type 1a supernova is the same. That makes these kinds of stellar events a reliable standard candle to measure distance. The scientists found that, once again, the Hubble constant was 73 kilometers per second per megaparsec, with an extremely small margin of error. And now we come to today. We have precisely one observatory that can improve on Hubble's measurements and tell us once and for all what is going on. This week, scientists using JWST confirmed that the Hubble Space Telescope's measurements are accurate. Now, this isn't the first time that JWST has double-checked Hubble's work. Back in 2023, JWST confirmed that Hubble's measurement of Cepheid variable stars were accurate. Because it is an infrared-optimized telescope, JWST can see through gas and dust that might obscure these stars, and its precision and accuracy and the level of detail you can observe with makes it easier to distinguish Cepheid variables from the light of surrounding stars. But this new survey, which was published in the Astrophysical Journal Letters, is huge. Scientists used JWST to survey over 1,000 Cepheid variable stars and 8 Type 1a supernovae. They've looked at every single measurement Hubble took, and the Hubble Space Telescope's measure of the Hubble constant stands. The Hubble tension is alive and well. So now what's next? Honestly, we've barely scratched the surface here. We've finally established beyond a doubt that the problem exists and isn't some sort of measurement or observation error. Now we can start looking at the whys. And if you're wondering what that third method, the gravitational wave method, tells us about the Hubble constant, that reading lies in between the CMB and supernova observations. It could be reconciled with either given the error range. The key to the Hubble tension is that CMB is left over from the Big Bang, whereas the observations of astronomical phenomena are from the more recent universe. It's possible there is something fundamental about that early period of the universe we don't understand. And to be clear, there is a lot about the early post-Big Bang universe that we do not understand. Or there's also a theory that the rate of expansion of the universe is actually constant and any changes within it are due to an unequal distribution of matter. But it's important to note that this goes against a fundamental principle of the standard model of cosmology. Whatever it is, scientists will continue to study the Hubble tension, and if we find the answer, you can bet it'll be big news, and I will definitely talk about it. Thank you for watching. I am Swapna Krishna, and this is Ad Astra.